Welcome to ECE CS 552 lecture on floating point. In this lecture, we'll talk about the floating point representations, the floating point data type, and briefly about hardware that implements floating point addition and multiplication. Once again, these are not crucial topics for the project, where you're not going to be expected to implement any floating point hardware. Floating point is a data type that's necessary when you want to represent a large range of numbers, larger than the range that you can implement with the kinds of fixed point or integer representations that we've talked about, which allow you to represent values in the range of -2 to the n minus 1 up to 2 to the n minus 1 minus 1 with n bits. Now, the trick for floating point is that we sacrifice the exact precision for that range by providing an exponent value that allows us to shift the relative weight of each bit position. What this lets you do then is it lets you specify a very broad range, which of course is the objective here, but you're not able to specify every discrete value in that range anymore. So floating point is very similar to scientific notation, which you might remember from your earlier education. So for example, the number 3.14159 times 10 to the 23rd can be expressed in scientific notation quite concisely, whereas if we wanted to express it without scientific notation, we would have to put all of those trailing roughly 20 zeros after that 9. We'd consume a lot of space. In terms of computer system terminology, we'd consume a lot of memory just to represent that single number. Instead, we can express it much more concisely by using this exponent notation that scientific notation relies on. So in floating point, we still use a fixed number of bits, but we partition them out so that we're using a single bit to represent the sign. That would be the leftmost bit. We'll use a small number of bits to represent the exponent, and we'll use the remaining bits to represent the fractional portion or significand of the number. And we interpret this representation using the following equation. We raise -1 to the power of s. So if s is 0, then it's a positive number. If s is 1, then it's a negative number. We multiply that by the fractional portion, and we multiply that by 2 raised to the exponent e. So again, because this is binary now, we're not going to use powers of 10 in the exponent. We'll use powers of 2 instead. This representation is standardized by the IEEE and the IEEE 754 standard. There are 2 variants of it, a single precision, which is 32 bits in size, and a double precision, which is twice as big, 64 bits in size. We'll only really discuss the single precision case in this lecture, but all of the principles that we cover are equally applicable to double precision. It's just that you essentially get more bits for the exponent, so you can represent both larger and smaller numbers, and you get more bits for the significand, so you can actually provide more precision for those numbers as well. The exponent in a floating point number expressed in this format is specified in what's called a bias notation or excess notation. The motivation for this is a little bit esoteric. The basic idea is that we can simplify the process of sorting numbers, whether they're floating point numbers or integer numbers. We can essentially use integer comparisons to sort them in rank order based on the size of the number. And that works perfectly well as far as putting the sign bit on the leftmost bit position, because the sign bit is interpreted the same way that it is for signed 2's complement numbers. That works well. But if we were to implement the exponent using a 2's complement representation, we would end up in a situation where a large number would have a positive exponent and a small number would have a negative exponent, and the sorting would not follow naturally in terms of just simply looking at the interpreting the underlying bits in that representation as a 2's complement number. So if we wanted to sort numbers, we would actually have to use floating point comparisons to determine their relative order, which historically was an uncommon feature. You didn't necessarily get floating point hardware when you bought a computer. That's generally speaking not true today unless you're buying a very low-end microcontroller that might not include floating point hardware. So this seems like kind of a silly concern in this day and age. But back when the standard was being defined, it was a fairly important constraint to be able to actually sort lists of floating point numbers without having any floating point hardware to support that sorting process. So what do we mean by an excess or biased exponent? Well, this table compares two possible representations for the decimal exponents shown in the left-hand column, ranging from, let's say, -127 to +127. In 2's complement, we can represent those exponent values using 8 bits in a form that you should be quite familiar with at this point in your career. The alternative that we can use, and which in fact the single precision IEEE format uses, is something called XS127. And all that really means is that you're going to take the actual exponent value, you're going to add an excess or bias of 127 to it, and then that will determine the unsigned binary value that you actually store in that field in the single precision representation. So in that case, the actual exponent -127 would be stored as all zeros. The actual exponent +127 would be stored as all ones with a trailing 0, which corresponds to the value 254. So for the 8-bit exponent that's in single precision floating point, the bias is exactly this 127, not shown here, but it sort of follows by extension. The bias for the double precision format is actually 1023. So what you see happening here is then if you actually do straight integer numeric comparisons of numbers where the exponent is encoded in this form, you see that small numbers have an equivalent, what you would think of as a small binary number representation in the upper bits, and large numbers will have what looks like a large binary number from a straight interpretation perspective, which allows us now to sort these numbers in magnitude order without having to expressly consider the fact that they are actually floating point numbers and not integer numbers. Another important feature of floating point numbers is that by convention they're stored in what's called normalized form. What do we mean by normalized form? Well, normalized form simply means that there's a fixed position required for the radix point for the number representation. So why do we want to do this? Well, if we think about, in general, scientific notation or a sign exponent fractional portion representation, we can represent the same numeric value in a number of different ways. Right? As you can see from the examples here, 1 times 10 to the 5th is really numerically equivalent to 0.1 times 10 to the 6th or 10.0 times 10 to the 4th. Having multiple valid representations for the same numeric value makes comparison operations difficult. You can't just check to see if the bits are the same. If the bits are the same, yes, you know that the two numbers are the same, but the bits could actually be different, and still the underlying numbers could be the same. So you can't check for equality very easily. You, in fact, again, have to have floating point hardware to enable that kind of comparison. So to avoid this problem, we prefer to have a single representation, and the single representation is enabled by forcing a normalization step to occur for all floating point numbers before they're stored or saved. And the normalization convention is that there's going to be only one digit to the left of the floating point radix, and it has to be a 1. There's really only two choices, a 0 or a 1. It makes perfect sense to make that requirement be a 1. And you get an additional benefit out of this decision to normalize the numbers. Since that leading 1 is implicit, we don't actually need to store it in the binary form. So we can just assume that it's there. We don't have to reserve a bit for it, and we get one additional bit of precision for our number representations for free. Just like we talked about for integer representations, we have to worry about overflow. Overflow is analogous to integer overflow, and what that really means is that the result of some arithmetic operation that you've performed is going to be too big to represent in either the single precision or the double precision format, whichever the programmer has specified. What that means is really, in the case of floating point data, that the exponent is too big. It doesn't fit into either that 8-bit or that 11-bit field that is available for for storing the exponent in the single precision and double precision representations. There's an analogous problem on the other end too, where the result is too small to represent. That's underflow. And here again, what that means is that the exponent is too small or too negative. We aren't able to represent it. Both of these conditions need to be detected, and they both need to optionally raise an exception if you're implementing standards compliant, IEEE 754 standards compliant floating point hardware. In addition to this issue with overflow and underflow, there are a number of special cases that have to be dealt with when you're looking at numbers that are specified in IEEE compliant form. So this table kind of summarizes all those possible cases. By convention, 0 is actually a special case for floating point. If the exponent and the significand are both exactly 0, then what that means is we're representing the actual value 0. Skipping over the denormalized case for the moment, the third row here shows that if the exponent is between 1 and 254 and the significand bits are whatever they need to be, then we're looking at a floating point number interpreted according to the rules that we've already discussed. The last two rows show two special cases. If the exponent is 255 and the significand is 0, that's used to represent infinity. So a number that, again, is large. The result of whatever computation computed that result is larger than can be represented, so it goes to infinity. Similarly, if the exponent is 255 but the significand is non-zero, that's defined as not a number. So that's a result that arises when you do an illegal operation, like let's say a divide by 0. You end up with a result that can't really be represented as a number, and the IEEE standard flags that using this representation. Okay, so those are fairly straightforward to understand. Let's talk about this denormalized case. So this denormalized case was a highly contested feature that several vendors who were participating in the standardization process when IEEE 754 was being formalized really didn't want this. And the reason for it is that adding support for these denormalized numbers actually complicates the control logic for the hardware that implements these arithmetic functions significantly. And these denormalized numbers are really there as an effort to squeeze just a tiny little additional bit of range out of the representation, and they're denormalized because in fact these numbers are not in the standard normalized form, and these can be the result of a computation where you end up again with a number that if you stuck to the normalized form you wouldn't be able to represent it because your exponent would need to be too small. So instead, what's allowed to be done here is, in this case where the exponent is 0 and the significand is non-zero, the number is to be interpreted as if there is no leading 0 or no leading 1 on the left-hand side of the floating point, and in fact the radix point or floating point is still fixed there, and then there can be any number of additional leading zeros until we finally get to non-zero bits somewhere in the significand. So if we were to normalize these numbers, you can imagine that the exponent would need to be even more negative than it already is at its max biased value of 0. So these would not be representable. These numbers would not be representable using the standard format, but they are allowed in the standard, and they do cause serious headaches for designers of floating point hardware. Rounding is an important topic in floating point, and to first order it's really important because even if you make small errors, because you have a limited amount of precision that you're operating with, those errors may seem very small, but they tend to accumulate. There are cases where even very small errors will lead to very large errors over billions of operations. So it's important that we, as part of the standard, very clearly defined the precision that the standard guarantees, and any implementation has to adhere to that level of precision. And that precision is enhanced by a couple of, actually three additional bits that are added to the computation as it's being performed. So as arithmetic operations are being performed, there's an additional guard bit that always gets computed beyond the 23 required bits of precision for single precision and 52 bits required for double precision. And the guard bit basically allows you to either round up or down appropriately. Now beyond that guard bit, there's an additional round bit, because it turns out that when we multiply two numbers together, we may end up with a leading 0 bit. And to, again, normalize the result so that we have a 1 to the left of the radix point, we're actually going to take this guard bit and shift it into the actual result, and now we no longer have a way to round the guard bit correctly up or down. So to enable us to round that guard bit, we actually leave an additional bit, or compute an additional bit beyond that bit, to guard against incorrect rounding in that case. And then to finally guard against the case where there are additional bits that are effectively sort of lost, and this happens when we're doing addition on floating point data, we have what's called a sticky bit. And this sticky bit is simply a summary bit that is set whenever we, as a result of the shift, have lost a 1 bit anywhere to the right of the rightmost bit, which is the round bit that goes beyond the guard bit, that goes beyond the required precision. So if there were any bits in the operand that fell to the right of that before the shift occurred, then the sticky bit will be set. And then the sticky bit will be used as a tiebreaker to differentiate between two numbers, let's say 0.5 and 0.5, with, again, some trailing bit out there somewhere, which makes it slightly greater than 0.5. So this can be then used to resolve ambiguous rounding scenarios into the correct direction. So let's move on and talk about the actual process of doing some of these arithmetic operations. We'll just talk about addition and multiplication in this lecture. So floating point addition is just like adding numbers that are expressed in scientific notation. The first thing you have to do is make sure the decimal points are aligned. Then you're going to add the significands together, and then finally, if the result has anything other than that leading 1 to the left of the floating point, then we have to normalize it. So that there's an example shown here in decimal, but it's really equivalent. The equivalent thing is what happens in binary. So here again we have two numbers, 9.997 times 10 to the second and 4.631 times 10 to the minus 1. In order to add these, we have to make sure the radix points line up. So what that means is we have to shift, in this case, the second operand over, and we have to increment its exponent by the amount that we shifted by. So that's what's happening there. And then we simply perform the addition, and what do you know? In this case, the sum ends up being such that there's more than 1 digit to the left of the radix point. So to normalize that, we have to shift to the right by 1, and as we shift to the right by 1, we also increment the exponent by 1. How do we do all this in hardware? Well, it's a fairly complex piece of hardware. We're just going to walk through this at a fairly high level. Again, walking through the functional steps that we talked about more or less already. So the very first thing that we have to do when we have two numbers presented to us that we have to add together is we compare the exponents. So we have a small arithmetic logic unit that computes the exponent difference, and then this exponent difference is used to generate control signals that will appropriately choose either the left or the right operand to get fed to the shifter, and the other operand that gets routed to the other input to the ALU. The inputs are also generated to generate the appropriate amount of shift that, again, is based on the difference between the two exponent values coming in. Now we have properly aligned numbers coming in. We feed them to the arithmetic logic unit, which adds the two numbers together. This is just a standard binary adder like the ones we talked about in a previous lecture. Once the result comes out, we have to do the normalization step. So here again, we have to have logic that looks at the result, makes a determination as to whether the result needs to be shifted in one direction or the other. In the case of addition, we can end up with a result that has 2 digits to the left of the radix, so we have to shift right. We can also end up in a case where the digit to the left of the radix point is a 0, which means we have to shift left. So depending on the result that has been computed, will then trigger a shift in one direction or the other. We also have to correspondingly then increment or decrement the resulting exponent value for the sum. So that's all. Those are all the things that have to happen in the normalization step, and then the final rounding step, we essentially look at the starting from the least significant bits, decide if we need to round up or truncate depending on the values of the guard, round, and sticky bits. Once we've finished all that, then we have the final computed significand exponent and sign. Next, let's talk about multiplication of these floating point numbers. Ironically, it actually turns out that the hardware for doing multiplication is significantly less complex than what's required for addition, and the main reason for that is that a very expensive piece of hardware that's needed for addition is that shifter that allows us to align the radix points between the two operands. That actually requires an awful lot of wiring and an awful lot of real estate. In multiplication, we don't have to do that, as you probably remember from multiplying numbers that are in scientific notation. You simply just multiply the two values together, and that's all you need to do, or the two fractional or fractional portions. And then to determine the exponent, you simply just add the exponents of the two numbers. And then finally, to compute the sign, you're just going to exclusive OR the two sign bits again from the two numbers being multiplied together to determine the sign of the product. Really, the only tricky thing here is that since the exponents are represented in this excess or bias notation, when we add two exponents together, both of which are biased, we end up with a sum that has double the bias in it now. So to correct for that, we actually have to remove that out. So that's what's shown with the expressions here in the middle of the slide, is that to compute the final exponent for the product, we add the two biased exponents together, but we then subtract one of the bias values out so that we end up with the correct amount of bias in the result. The significand computation is very similar to the integer multiplier that we talked about before, except that in floating point hardware you typically have the combinational version of it rather than the sequential version. So it's just a standard multiplier, array multiplier, again, either for 23 bits or 52 bits, plus the guard, round, and sticky bits, depending on the precision that's required. And it's again implemented with a Wallace tree of carry-save adders to add up all the partial products. Functionally, then, what needs to happen to implement floating point multiplication is we need hardware to compute the sign, which is just an XOR gate, the exponent, which is just an adder with the bias remove logic for removing the excess bias, and then finally the multiplier array for computing the significand. However, once again, we need to normalize the results. Of course, we need to also check for overflow and underflow. We need to round, and potentially after rounding, we might have actually a carry that sort of ripples all the way through the product, and we may have to normalize again if necessary. But that's basically it. So those are the steps that you need to implement floating point multiplication. So just summarizing this lecture, we talked briefly about floating point representations. We talked about the need to normalize the results. We talked about overflow and underflow and rounding. And then we very briefly covered at a sort of a block level diagram level of detail, hardware for doing floating point addition and floating point multiplication. We glossed over an awful lot of details here, but again, really getting into the nitty-gritty details of how this hardware really operates is well beyond the scope of this introductory course.